Hi folks, today's topic is area between curves. So a couple of things to remember. First of all, area is always positive. So what we're going to do today, our goal is to be able to look at a region that's bounded by two curves and calculate the area in between. So all the stuff that we've been doing up to this point involved one curve and then usually the x-axis. So maybe we were above the x-axis or below the x-axis. Now we're adding that extra curve. So our goal by the end is that we should be able to integrate using integration, figure out a way to calculate that area between these two curves. So a couple of things to remember. We're going to use the top function, subtract the bottom function to find the distance. So this is going to be so like for instance, let's say we did our old way. Let's say this was our curve f, and we'd find the area under the curve, we would stop here. Well, now we're going to take this function value, that's the height of this rectangle, and now we're going to subtract the height of this rectangle. Well, what's the area of this rectangle? Is going to be negative. So when I subtract that, it's going to give me this total distance, this total area, this total height. Same thing over here, but in kind of the opposite way. We have this height here, but this time our this curve, the area underneath the curve is above the x-axis, so we want to subtract off that little area underneath the curve. So in this case, let me try this again. So in this case, I want to take this area, and I want to take this area. Now this area is negative, so when I subtract that negative, I actually add it on to that, gives me the overall area. Well, if we look over here, now we have an area that's underneath the first curve, would go all the way down to the x-axis, but then we're going to subtract off this area here, and that's going to leave us this area here. So this area we're going to subtract again, but this time it's going to be a positive, which is going to leave us with a smaller area than we had before, where this one, I took this full area and then I subtracted this negative area, which actually gave me the total area, added those areas together. So hopefully that makes sense. We're going to talk a lot about what's called a representative rectangle. This would be a representative rectangle, but we just can draw it with just a single line. I mean, we don't have to draw it super thick. You can draw it maybe with two really close lines. So in this case, if I wanted to figure out this area, I'd have to take the area under the curve of the upper function or the top function, and I would subtract the bottom function. Now this gets more interesting when those roles switch. If we would have continued this curve, let's say that there's another area over here. Now this one's the top and this one's the bottom, but we'll talk about that as we get there. All right, area of the region. He talked a little bit about this. I agree. We shouldn't call that A. We should call that area. I know it seems like a minor detail, but remember, we're going to use big A, to represent anything that we store in our calculator. So we don't want to get those two things confused. A couple of steps here. Draw a picture. Identify the region. Decide how to slice. Find and identify any intervals. In other words, where do they intersect? And then set up an equation for our representative rectangle. Let's give it a whirl. Right off the bat, no calculator. That makes my math voice a little bit sad, but that means that we've got some functions that are easy to graph and easy to integrate. So I'm going to encourage you to start off by sketching these without my help. Hopefully you know what the e to the x graph looks like. You better know what the graph x looks like. I'm going to come hit you with a tack hammer. All right, let's see how you did. So e to the x, that's our exponential growth problem. Starts low, hits here, launches up. I'll leave myself a note. E to the 0 equals 1. So that's at a height of 1. I know that much. I know that x is 0, so anything to the 0th power is 1. Then I'm going to sketch the y equals x curve. That's a nice, oops, I need to make it dashed. That's the nice 45-degree angle. This is 0, 0. Okay, now look, if you just tried to calculate the area bounded by these two curves, the answer right away I know is going to be infinity. Because look, this goes this way, right? This levels off over here, and it would keep leveling off this way forever. This would go down forever. So what's happening to that area in between? It's getting infinite. Same argument at that end. So they had to bound it by a couple other lines. These vertical lines, x equals 0, and the vertical line, x equals 1. So I'm going to sketch in here x equals 0. Then I'm going to sketch the line x equals 1. I don't know exactly where that is, so let's just estimate that it's here. And let's make sure that our graph is drawn correctly, because I just kind of sketched it. How do we know that this doesn't get underneath there? Well, let's just test this value. When I plug 1 into the x function, I get 1, so this is a height of 1. When I plug 1 into e to the x, I get e to the first, which is 2.718, whatever. So yeah, we're okay. So our region is going to be this place, bounded by those two vertical lines and then these two curves. So that's the region that we're looking for. Let's start off by drawing that representative slice thing. So you're basically trying to draw a super tiny rectangle inside of this, which there's my representative slice. And I like to write usually dx next to that, because that's how wide that section is. I should probably, maybe I should label these. Y equals, f of x equals e to the x, g of x equals x. That's what we call a representative slice. Representative slice. I don't know why Corpy pushes it so much, but he does it every single time he draws one of these regions. No calculator, but we do get to verify on our calculator to see if it's correct. I don't know if I'm going to actually, yeah, I mean, we can type it and it won't take long. All right, so let's see now. We've got to take and look, first of all, to decide if there's any spots where one function is on top and then it switches to the other function being on top. And if you look here, the e to the x function is always higher than the x function. So we don't have anything super tricky in this one. We can just go ahead and start to evaluate. So my area, notice I'm spelling out the word, not just using a equals, is going to be all of the areas underneath the x to the graph, take away all the areas underneath the x graph. So that would be the integral of e to the x subtract x. What am I integrating according to? Don't forget this part, dx. So this was our upper function. This was our lower function. And then we also want to integrate from we've got to actually define where this region runs. So we're going according to x, so we've got to look at it from an x perspective. So what's the left end, or what's the low x? The small x is 0, and we go over here until x equals 1. So like I said, this is a non-calculator. I'm going to encourage you to pause and try to integrate this. Let's see how you did. Integral of e to the x is e to the x. Integral of x is x squared over 2. This is a definite integral, so I need to define it from 0 to 1. I can plug and chug. E to the 1 minus 1 squared would be 1/2. Minus e to the 0 minus 0. So that's what? E minus 1/2. E to the 0 is anything to the 0 is 1. So e minus 1/2 minus 1, you could do 1.5. I'm going to do 3/2. What else did I want to leave a note on? Anything I wanted to remind you of? If you're looking, this would be, you probably wouldn't get one this easy, but this is the important stuff. This is the important kind of big idea. The rest of this is just your skills of being able to integrate a definite integral. But being able to write this is the big idea. So once you get that idea, things are good from there. It says to compare. If you want to compare, grab your calc. You'll see that it works. All right, so find the area of the region enclosed by y equals x squared and y equals 2x minus x squared. So I'm going to encourage you again. I'll give you a hint. You kind of want to draw this one a little bit bigger. Encourage you to try to make a sketch here. Pause it if you haven't. All right, let's see. So x squared, that's pretty easy. X squared is going to start here. It's going to be a parabola. So something like this. That's y equals x squared. This is going to take a little bit more work, but not too bad. We know that's a parabola as well. It's a parabola that's pointed downward because we have a negative in front of the x squared. What we need to figure out is where does it cross the x-axis. So I'm going to try to figure out where the zeros are. The zeros are wherever 2x minus x squared equals 0. We can now solve that by factoring out an x. We get 2 minus x equals 0. Now we would ZPP, and we get x equals 0 or x equals 2. So on my graph over here, I've got one at 0. Then I've got, I'll change my color. This is black. Over here at 2. Then we've got another intercept. So our graph looks something like that. I could probably get more specific here. That's going to be at the point 1, and I could plug it in, or I could do the over and up kind of that we talked about. I don't know if you remember that from the way parabolas move. But this should be good enough because I now have seen the region. I now know where the region is. And again, it's not over here and it's not over here because what would happen to those regions? They would go on forever. They'd be infinite, right? This area just keeps getting larger and larger and larger as we go to the side. So you got to kind of interpret a little bit of what's going on. And then I like to draw that representative rectangle in there. That's at a width of dx. That's what that dx means. That's how wide it is. And then the height, we could write a little bit more this time. So that height of that curve, how high is that curve? Sorry, let me try again. How long is this distance here? Well, it's the distance all the way up to the green. Take away the distance up to the pink. So that would be the distance. What did we call this? We would call this, no, we didn't really. I could call this y2, call this y1. So this would be the height of this, the height of my function, is equal to the y2 function minus the y1 function. If you want to write all that, to kind of help you understand the way it looks, it's up to you. If you can go ahead and write your integrals up, that's fine as well. Well, let's try to write up our integral right now. So we need to integrate from, so my region starts from the left. Dang it, I want to get in this habit of writing area first. This is the area that we're calculating between these two curves. Starts at 0 and it goes until, there. Do we know where there is? No, we don't. We don't know for sure. Maybe you already estimated, but I've got to figure out where these two things intersect. So now we've got to find the point of intersection between these two curves. Because I have to figure out where that region stops, right? I know it starts at 0, but I need to stop where. So let's go ahead and use our, how do we figure out where two functions intersect? What could we do with the equations for the two functions? And set them equal to each other. I would add this across. Actually, I'm going to go this way. Solve this by, I'm going to do a factor out of 2x. That's 1 minus x. ZPP, I get x equals 0 and x equals 1. So these now are my points of intersection. And that kind of makes sense up here that crosses at 0. I didn't know that it crossed at 1. I guess my line is really not very well drawn, but that happens in mathematics sometimes. I'll scribble that out and I'll change that to a 1. Yikes. Intersect x equals 1. So let's bring that information now back to our integral. Our area is the region from 0 to 1 now of, and I didn't define, I guess I kind of defined them. So if you wanted to use your y's, but we've got to do this by hand anyway. So I'm going to actually figure it out here. So what's my upper region would be 2x minus x squared. Do I need these parentheses? Short answer is no. I mean, what's in front of this is a positive, so you can get rid of those. In the next one, do I need parentheses? The answer is still no. Now, I like to write them there because it reminds me that I need to distribute this negative, but because this is only one term, I actually wouldn't need to distribute that negative at all. I mean, when I distribute it, it just becomes negative. I shouldn't say I don't need to distribute it. So that's 2x minus x squared is minus 2x squared dx. Now let's integrate. So that would be 2x squared over 2 minus 2x cubed over 3 from 0 to 1. So those are going to cancel. I can kill those off. So let's see. Plugging in 1 would leave me with 1 squared, which is 1 minus 2/3 minus 0 minus 0. Well, what's 1/3 minus 2/3? 1/3. So that little area between those two curves is 1/3 whatever your units are in the story. And luckily they didn't give us any units, so we don't gotta sweat them. What do you think? I actually like this stuff a lot. This is, to me, very intuitive. Fits, goes straight forward. I like it. Yay! My math voice, yay! Calculator permitted. Find the area of the region bounded by blah and blah. Well, it's up to you. I guess you don't have to sketch it, but man, it sure makes your life, your ability to visualize way easier. So I'm going to try to draw. Now this would be one that I wouldn't even try to sketch by hand because I have no idea what that's doing. I could maybe do that. I know it's a quadratic, or excuse me, a quartic, but that minus x is really going to throw some curveballs at me. So I'm going to go through, oops, I got some stuff on here. Do a zoom 6, get me back to the normal. And I'm going to input these now as my functions. So alpha, give me my fraction bar, x on the top, square root x squared plus 1. And then x to the 4th minus x. So I did a zoom 6 first to give me a window. Not the best window. You can adjust your window by hand if you wanted to. You know how to go into window and start to play around. But there's some other tricks. You could do a zoom here, and there's two zooms that I want to show you. There's zoom in. Actually, I'll do a zoom box first. So zoom box is the very first option. Zoom box, it's kind of tricky. You got to move your cursor to one of the corners of the box that you want to draw. So now when I hit enter, then I start to move to the left, and then I move down, it creates a box around that region. And then I hit enter again, and it will now zoom in around that boxed in region that I found, that I boxed in. Which I think that's a good enough picture to sketch on my paper. But I want to show you this other method real quick too. So let's go back to a zoom 6. So right away, you know, you don't have a great window, and you don't really need a perfect window. And so you're like, I don't need to mess around with my zoom too much. I'm going to go to zoom in this time. And this time, just take your cursor, see that little cursor there, and move it to where you think is the very middle of that region. So just kind of get it. I'm kind of guesstimating that I'm in the middle of that region. and you hit enter, and it'll zoom in right around that area that you left, or sorry, where you left that cursor. So both of those were good enough for me to get a decent sketch on my paper. So what do we have? We have one curve coming in like this, and it goes down, and then it goes up. And I got this other curve coming in like this. It looks like it hits at 0. We'll check that because we can use our calc. And I want to label these so that I don't have to keep looking up at the equations or back at my calculator to know which is which graph goes with which equation. No, oh, I got them backwards. Don't I? Yes. So here's how you can check. So this one is in Y1. When I hit graph and I hit trace, you see how it's on Y1? So that curve is the Y1. So this is f of x. And this is g of x. All right, and then the area that we're trying to find, that area, and I always draw one of those representative slices just because I don't know if that's worth a point on its own or not. So I'm going to draw it because it takes 2 seconds. Now, the height of this, if you want to, h of x would be equal to, now does the height change for either one of these? No, it stays as f of x is always the upper and the lower. So our h of x equation would equal f of x minus the g of x equation. All right, let's see if you can do this on your own from here. All right, let's see how you did. So you should have said area equals the integral from, okay, wait, now we got to figure out where this intersection is. So I'm going to draw a little arrow here. One of my intersections is this spot right here. Now the way I do this is I go second calc intersect, enter, enter, you hit the first two, and then when you get to the guess, you can guess wherever you want, and I think they intersect at 0. So I'm going to hit 0, and yet we get one intersection to be 0, 0. So what's the left end of my region? That's 0. Now we've got to find the right end. In other words, we've got to find this point now. What's this point of intersection? So I'm going to go back to my calc. I'm going to go to intersect. First curve, enter. Second curve, enter. And then when it says guess, that's when you're allowed to type stuff in. So I'm thinking this is like around 1. I know it's not 1 because, or I don't think it's 1 because that's 1. Yeah, it's definitely not 1. But let's see if it's near. I know it's near 1, and it's 1.0. Now, before I write this down, actually, I am going to write this down. I'm going to write this as 1.180, comma, 0.763, and then I'm going to write equal to a comma b. Now what that means is if I ever need to use either one of these, I'm going to store these as the letters a and b. So let me do a quick review on how to do that. So after you find the intersection, leave that in there, quit out of this, hit X, store it as a. So there's X is now a. Remember they're at 1.180. Now alpha y, which is above 1, way down here, alpha y, we want the y and we want to store that as alpha b. And so now b is stored as 0.763. Now in this case, we're not going to actually need this one, but I just wanted to show you how you can store stuff. So let me get a different color. I kind of wish that I don't know why I used yellow and then a yellow again. I think it gets confusing. So let's go now to our actual integral. Area is equal to the integral. Left bound is 0. The right bound is that spot that we find, and I'm going to call that just a. If you want to write down 1.180, that's fine too. But it's going to be a lot easier now that we've stored this as a to just call that a from here on out. Okay, what's the order of my functions? Who's the upper function? That's f of x minus who's my lower function, g of x. How come I still lost a point? I look really nice and neat, but I still got a point off. My variable of integration must be written. Okay, so from here, they say we can use our calculator, so I'm not going to overthink this. Did I store these? Yes, good. Okay, so this is going to be y1. This is going to be y2. So I can quit out of here, clear, clear, clear. Math 9, I want to go from 0 to a, dang it, 0 to a, and I want to take f of x, which was y1, so alpha f4 y1 subtract alpha f4 y2. Okay, what are these equations based on? Even though it says y here, remember those are pulling from our equation y equals x stuff. So we're still integrating according to x. Type all that in and we get 0.785. We don't have any units in the story, so we don't need any units. But whatever they would be like something squared. All right, let's have you start off. Calculator permitted again, so math voice is yay, but usually that means it's kind of tougher, but at least we get to use our calc. Got that little safety blanket there. Let's see if you can do up to, let's see if you can at least get the graph going. You should be able to do that. All right, let's see how you did. Now, there's plenty of room here, so I'm going to kind of draw my graph a little bit big. For once Corpy left us plenty of room to write. Could I graph these by hand? I could do this one by hand. I couldn't do that other one by hand, so I'm going to input these in my calc. So what is that first one? At 3x cubed minus x squared, subtract 10x. And then my second equation is 2x subtract x squared. All right, let's see. Crappy window. I'm going to stop. Anytime you want to stop in the middle of your calculation, just hit the on button. So look, like it's graphing right now, and I don't want to wait for it to finish, so I'll just hit on. And I'm going to do a zoom 6 first to see what kind of window zoom 6 gets me. Probably good enough. I'm going to do a quick zoom box just because I think I want to review it with you. So I'm going to move this one. Actually, I'm going to go this direction. I want to get that little intersection down there, so I'm going to go a little bit past it. Hit enter. Stretch all the way up. The other side and stretch all the way over. Now let's see what our picture looks like. So this is the cubic function. Then there's the parabola, the quadratic function. So now I can make a sketch. Let's say this one goes, it looks like it goes through 0, 0, but we'll check that. There's one curve. Now let's see what our other curve would look like. Down here it intersects somewhere. It looks like it hits at 0 and at 2. I think we actually already solved this, so those are the intercepts for sure. Let's label these. This is g of x. That's my parabola. This is f of x. Now in my calculator, I called that y1. And in my calculator, I called this y2, just to sort of keep track of stuff. Do we have an area in between that we could highlight? Absolutely, right? This region. This region. And then we don't want to include over here because those are all infinite. Those are not considered bounded by the region, by the curves, I'm sorry. So what's interesting about this one? Hopefully you notice as we try to write up, all right, so let's see. Well, we got to figure out where our intervals start. So we've got to figure out this spot, and we got to figure out where it ends. So let's quickly figure these two values out. Hopefully it's going to be nice. Second calc, intersect. Remember, you can hit enter, and then when it says guess, you can guess where that is. I think it's around -2. Let's see if I was accurate. Yep. This is the place -2, -8. I don't need to store that as anything. I can plug in -2 and -8 if I need to. Let's find our other intersection. Our other intersection, second calc intersect. Enter, enter. So and then once it gets to guess, I think that's going to be at 2. Yep, it's at 2 comma 0. So when we start to integrate this thing, area, change color, area equals the integral from, this region starts at -2, and it goes to 2, right? Of, okay, which one's my upper function? Well, my upper function, oh, wait a minute here, look. In this region, the upper function is f, and the lower function is g. But when I move to this region, the upper function is g, and the lower function is f. We've got a problem. What are your thoughts? How do you think we could get around this? Well, hopefully you said we could take our region, and instead of going from -2 to 2, we're going to break it up into 2 separate integrals. Instead of one big integral for the whole problem, we can't do that because our integral is supposed to be one function minus another function. But because our upper function switches from one region to the next, we need to define it differently. So now we need to find this new place of intersection. Where is this intersection? I'm guessing it's 0, 0, but let's make sure. Second calc intersect. Enter, enter, and then guess. I think it's at 0. Yep, it's at 0, 0. Now remember, sometimes you'll get that weird e to the -14 or something like that. So, by the way, if you don't want to do guess, intersect, you move the cursor. There's 3 intersections here, so you got to move the cursor as close as you can to the intersection that you want to find. So like I moved it there, enter, and then the enter, and then the enter again. You can do it that way, or you can just guess like I did. Well, let's try to write up our integral now. What does our integral look like now? So we're going to now say that the area is equal to, well, there's this first region, and that's the region from 0, my bad, where does it begin? From -2 until 0 of, now you can write the actual equation. If you had to do this by hand, I would probably write the actual equation, but because we don't, I'm just going to use the names of the equations. So the green one is my upper equation here, so that's f of x minus g of x. And then don't forget your d of x. Plus, then my next region starts at 0 and goes until 2, but now the upper function is g of x minus f of x. And don't forget your variable of integration. Pause it here if that didn't make sense. If it does, cool. If it does, cool. Grab your calc, start calculating. Now remember, we defined these as y and y1 and y2, so I don't have to actually type in all that mess. I typed it in once into my grapher, so I don't have to type it in again. So let's try this using the letters that I called this y1 and this y2. This would be y2 minus y1. So math 9, from -2 until 0 of y1 minus y2. According to what variable? Even though those are y's are dependent on x, plus math 9 from 0 until 2 of, oops, dang it, of y2 minus y1 according to x. Should get 24. Yeah. So our area is equal to 24. Well, let's try another one. Let's go. Nah, let's do the next one. Yeah, let's go. Actually, I'm going to start this next one with the next video.